Okay. Hello, everyone, and welcome to another session of our differential geometry webinar, AmSul. Uh, I would like to introduce to you Brian Grajales from la Universidad Estadual de Maringá, or something like that is pronounced, and who will talk today about inhomogeneous Einstein metrics on complex projective spaces. Okay, thank you, Brian.
Thank you, Adrian. I want to thank everyone to be here in this presentation. I want to thank the organizers too for the kind invitation. This is a very nice, a very good seminar. So today I'm going to talk about a current work I am doing with Professor Lino Grama from Unicamp y Profesor Anderson Araujo from the Universidad Federal de Viçosa, UFB. I'm going to talk about some inhomogeneous Einstein metrics on complex projective spaces, and I want to highlight or to point out that we are dealing with inhomogeneous Einstein metrics, but the metrics we are going to talk preserve some symmetries. We are going to consider an action, but not a transitive action, but a cohomogeneity one action. So as an overview, we are going to use a classification of all cohomogeneity one actions on complex projective spaces in order to try to find or to try to prove existence or not existence of Einstein metrics on complex projective spaces. So first I'm going to make an introduction. Maybe all of you are familiar with a lot of things I'm going to talk about here, but I want to introduce some historical review about Einstein metrics. As we know, the Riemannian metric is Einstein if the Ricci curvature or the Ricci tensor is a scalar multiple of the metric itself. And this is a classical problem that have been studied in many contexts, but I know on compact homogeneous spaces or non-compact even, there are many contexts in which we have a classification of homogeneous metrics. This is a problem that, as I know, is not done, is not finished, but you have a classification of or characterization of homogeneous Einstein metrics in classes, different classes of homogeneous space. For example, if you look at the complex projective spaces, you can view the complex projective spaces as homogeneous spaces, and the Einstein metrics that preserve the action, the transitive action, were classified by Ziller in 1982. So what about non-homogeneous Einstein metrics? Inhomogeneous is very difficult to pronounce for me. Okay, inhomogeneous Einstein metrics on complex projective spaces or in other contexts. This is a problem that it's quite different because when we are dealing with homogeneous metrics preserving a transitive action, this equation, this Einstein equation here, is equivalent or reduces to a system of algebraic system of polynomials, of homogeneous polynomials. So you can do, for example, you can use numerical methods, or you can use algebraic methods in order to solve the equation if you want to solve, or you can use another tools for analyzing properties about metrics satisfying this. But when you have for example, a cohomogeneity one action on a manifold, this equation is no longer an algebraic system, but a system of ODEs, as we are going to see later. So maybe you need more analytical tools to try to say something about the existence or some properties. But so, for example, on cohomogeneity one Einstein metrics were studied by Professor Christopher Bohm. I'm going to give the reference in spheres, in low-dimensional spheres, and other authors as Eschenburg and Wang have developed some theory or some results that help us to deal with this problem. Okay. So as I said, we are going to consider a manifold which admits a cohomogeneity one action of a compact Lie group. Okay. And we are going to see that in general, the Einstein equation reduces to a system of second order ODEs, okay, with boundary conditions. And so I'm going to give a review about how can we obtain this system of equations and how can we obtain the boundary conditions. Assume that we have a smooth manifold M of dimension n, and let G be a compact Lie group acting smoothly on n with any cohomogeneity and an action, a smooth action. So we are going to fix some notations. As usual, we denote for a point P in M, we denote GP, the isotropy group of P, and the orbit as GP, G dot P. See that we know this is homeomorphic or diffeomorphic if the action is smooth to this quotient, that G over GP. The orbit is a homogeneous space. And with respect with this action, we have three types of orbits. So we say that the orbit is classified into three types. The first one is principal, and we are going to say that an orbit is principal if this group, the isotropy group of any element in the orbit, is conjugate to a subgroup of any other isotropy group. So this group the isotropy group is minimal. See, it's minimal. It does not contain any isotropy group. Okay, we're going to say that an orbit is singular if the dimension of the isotropy group of Q is greater than the dimension of an isotropy group. But I'm going to explain this. So you have that all principal orbits, you have a result that all principal orbits have the same dimension. Okay? So the isotropy group of an element in a principal orbit have the same dimension. As we know, this group GP can be embedded or can be considered as a subgroup of GQ because it conjugates into all of it is conjugated to a subgroup of GQ. So in this sense, we have this extension, this quotient is have a dimension greater than 0. And we have another type of orbits that are called exceptional. And in this case, we have that an orbit is exceptional if this quotient is finite and non-trivial. This means that the isotropic group of any element in the orbit is a finite extension of a principal isotropic group. We are going to say that this is a principal isotropic group, this is a singular isotropic group, and this is an exceptional isotropic group. So I made a design, but not good. That we can think about this. We have the manifold and we have an action, and the orbits. Here is the blue lines. These orbits are the principal orbits because they have the largest dimension between the orbits. And we can think these 2 points over here as the singular orbits. Well, it could be exceptional orbits, but we are going to consider that that's not the case. There are not exceptional orbits. Okay. So in this case, we have this proposition. I don't have the exact reference, but because the original result is I think it's too old. But it says that if n minus d is less or equal than 2, the orbit space is a smooth manifold, possibly with boundary. And here, I didn't say, but this d is the dimension of any principal orbit. So as a consequence of this, we have that if this number n minus d is called the cohomogeneity of the action. So we have in the case that the cohomogeneity is 0 or the cohomogeneity is 1, the orbit spaces can be equipped with a differentiable structure. So it's a manifold, possibly with boundary. And this is good because when this is the case, we have geometric tools to work in here. Okay. Then we can focus on cohomogeneity one manifold. That is the principal orbits have dimension n minus 1, a dimension 1 less than the dimension of the manifold. So we have this theorem by Moser in 1957 that when the manifold is connected and has at least one orbit of dimension, one principal orbit of dimension n minus 1, then this orbit space is homeomorphic to one of the following manifolds with boundary. So we have 4 cases. The orbit space is homeomorphic to the circle as 1, to the real line, to the half line, or to the closed interval, any closed interval. So for example, when the manifold is compact, we have only the cases 1 and 4, and when the manifold is not compact, we have the cases 2 and 3. Okay. So in this design I made here, excuse me. For example, we can think that this is the manifold. We can construct a transversal section all over the manifold that is transversal to all orbits from here to here. So in this case, when we have an action that have this behavior, we can think the orbit spaces, and in this case would be a closed interval. This is the zero, the zero of the interval, the 1 on the interval, and the interior of the interval correspond to all the principal orbits. Okay, so what I say in all cases, the interior points correspond to principal orbits, while boundary points correspond to non-principal orbits. Could be singular or could be exceptional orbits. Okay. We are going to make some assumptions. The first assumptions is that the manifold is compact and the quotient is homeomorphic. in some cases we have diffeomorphic, to a closed interval. And we are going to assume that the manifold does not contain any exceptional orbits. So the boundary points are, in fact, singular orbits, corresponding, in fact, to singular orbits. Then what we are going to do now is to try to describe the Riemannian geometry of this manifold, keep with this kind of actions. Describing the Riemannian metrics that preserves the action. So what we have to do is to fix a G-invariant metric that is auxiliary, and we are going to consider a geodesic with respect to this metric that parameterize the orbit space in this way. Z from 0, 1 to the manifold, and C of 0 would be the singular orbit, as C of 1 would be the other singular orbit, and the interior points are going to be to correspond to principal orbits, to points on principal orbits. Okay. And we are going to denote for any t in the interior of this interval by H the isotropic group of the corresponding element. So this isotropic group is in fact a principal isotropic group. Okay, and denote by K the isotropic group of the singular orbit at t equals to 0. Okay. By some results, we can construct, we can conjugate this group H in such a way that H is contained as a subgroup of K. And in this case, one can prove that the quotient K over H is diffeomorphic to an sphere. In this case, it could be a zero-dimensional sphere, but since we are assuming that there are no exceptional orbits, then we have this quotient is of positive dimension. So L is greater or equal than 1. Okay, it's a result from the monster again. And how can we describe the G-invariant metrics on M? Okay, so the invariant metrics, G-invariant metrics on M are determined by its restriction to the union of all principal orbits. That means that in the design I made, you can define a G-invariant metric only in the blue lines without the singular points, and if I can extend that matrix to the singular points, then that extension is uniquely determined. So we can consider a G-invariant metric on the whole manifold as a metric restricted only to the principal orbits, to the blue lines. And the good thing is that the metric restricted to the union of all principal orbits takes this form: is G equals to dt squared plus gt, and this gt for each t, gt is a G-invariant metric on the quotient J over H. So you have let me give a little explanation here. So imagine you have the geodesic joining this point and this point. So the metric is you are going to consider the tangent vector to that geodesic as unitary and orthogonal to all these lines, to all these principal orbits. And the thing is that the action is transitive when you restrict to a principal orbit. So you have here for each t you have a metric GT which is invariant, which is in fact homogeneous in this principal orbit. Okay, so you have the metrics like this, and you have good news because we know from the theory of homogeneous spaces and so on that we can describe these metrics as inner products on for example an orthogonal complement of the Lie algebra of H. That is known. That is theory from homogeneous spaces, but I'm going to specify that. So if you consider, for example, G, K, and H, the Lie algebra, the corresponding Lie algebras of the groups G, K, and H, respectively, you can construct these invariant metrics by considering an B invariant inner product on G. You said this, and you can consider the orthogonal complement with respect to this B invariant metric in G, and say that is M. Then you have this reductive decomposition, and you can identify this M. As we already know, this M is identified with the tangent space of the principal orbit at the point, in this case, C of t, which is the origin we are considering. So here we know that these metrics G of t are nothing but inner products on M that are invariant under the action of the adjoint representation of H. Okay. But the thing is that we can decompose. Well, we are considering G is compact, so you have this isotropy representation of the principal orbit is completely reducible. So you can decompose this tangent space, this subspace M, into pairwise orthogonal, irreducible, invariant at H invariant subspaces M1 and S. But we are going to make we can construct a particular decomposition in such a way that each subrepresentation or each submodule is contained in the Lie algebra of K, or the intersection of the submodule with K with the Lie algebra of K is trivial. So, for example, you can define two subspaces, P and N, and here you are going to associate to take all the subspaces that are contained in the Lie algebra of K, and N would be the subspaces, the invariant subspaces that intersect K trivially. Okay? And these two spaces are important for describing the matrix. So, as I said before, this metric GT can be identified with an inner product invariant under the adjoint representation of H. And we know that since we are fixing this invariant inner product on G, there is an operator that in fact is positive and self-adjoint and equivariant with respect to the representation of H, such that this quality holds. So we can think about this G of t as a family of operators from M to M satisfying this. And we know how to describe this in terms of the reducible subspaces of M. So, for example, if all the submodulus are inequivalent as representations of H, we know that all these operators are diagonal, have this form. are determined by S parameters. S parameter, where S is the number of irreducible subspaces. So since we have a family and the metric is smooth, the metric is differentiable, then that implies that the functions, these functions over here, are going to be the differentiable or smooth. Okay. If, for example, we have some equivalences between these submodulus, we can have other types of metrics, but we are not dealing with that case in here, okay? Because in the example I'm going to give in the complex projective space, that is not the case, okay? Then this is a family of this family of functions. These f1, fs are defined, since the metric is defined only in principal on the union of principal orbits. Then that functions are not defined at 0 and not at 1. So the thing is, how can we extend these functions for to construct a metric in the whole manifold that with a good behavior at the singular orbits? So that problem is already solved by Eschenburg and Wang in 2000. And in a more general context, they gave conditions on the boundary to ensure the smooth extension of the metric of the G invariant metric. So we know that in this case, for example, we can give conditions on the functions, and it's the first order and second order derivatives to extend the functions to 0. To 1 is the same thing, because this is local. So the thing is that these conditions are difficult to write, and the answer is no, because in this paper by Eschenburg and Wang is very detailed, and you have if you understand the paper, you know how to how the conditions on 0 must be, okay? So for example, if we have this invariant inner product, if this inner product restricts to the standard metric of curvature 1 on this homogeneous space, which is the sphere, then we have these conditions on the functions fi. Okay.
What did you say about the other point, t equal to 1? Something similar has to happen?
Yes, you can use a very similar argument from this paper, and you know how to do that. Or maybe you can just you can do a reparametrization. For example, change t by 1 minus t and apply the same argument. So you have, for example, the conditions. You know how the functions must be, and the initial conditions.
Okay.
This would be important because, for example, when later we will see when we have the Einstein equation. That is a system of ODEs, but we have initial conditions. So it's like a Cauchy problem that it's not easy to solve in general.
Okay, thank you.
No, thank you. So, for example, now we are going to, we already know how the invariant metrics are on cohomogeneity 1 manifolds. We can use this proposition or this theorem by Group and Ziller in 2002. That the thing is they gave us formulas to find the rich curvature, the rich tensor on cohomogeneity in one manifold. So in this context, if you have to take an orthonormal basis with respect to the invariant product, and this basis must be adapted to this decomposition in the sense that you have a basis of M1, a basis of M2, a basis of MS. And with respect to that basis, you can compute the rich curvature using these formulas that are not easy. And here it's worth to point out that T is going to be the tangent vector to the geodesic C, to the transversal geodesic we are considering since we started. Okay, so we have these formulas for the Ricci tensor, and I want to say that this formula, for example, in our current work, we used these formulas to write the Einstein equation, because you have the Ricci tensor and you have the metrics, then you have the Einstein equation. But this formula also can be obtained using Riemannian submersions. I think this is well known, but I want to say that equivalence formula can be obtained differently with many ways. Okay. So here we are going to keep these formulas, and later we are going to see how can we write the Einstein equation for a cohomogeneity one action on a complex projective space.
Sorry, Brian, about this bracket with SIR.
Okay.
It's a combinatorial number or something like that.
Yes. I didn't put the formula here, but this is computed in terms of this basis, and it's similar to, I think the notation is like this, but sometimes it appears like simply as a word, ISR. But see, it's like a formula, combinatorial formula in terms of the basis, the Lie brackets, and the inner products. So we know how to determine these numbers.
So it's complicated.
And depend on the on the brackets. In general, I think it's complicated, but in some particular cases you can apply them.
Okay, thank you.
Thank you. So the thing is that we have the Ricci curvature. We can write this equation because we have the Ricci tensor and we have the metric, and we know this is. If you see here, you have all of these terms contains the functions fi, it's their derivatives and their second derivatives. So when you do this, you can see from these formulas, you can see that for cohomogeneity one manifolds, this condition reduces to a system of second order ODEs. And the boundary conditions are given by these boundary conditions, the ones provided by Eschenburg and Wang. And moreover, we have this nice result that says that in a cohomogeneity one manifold, there exists an asymmetric locally defined around each singular orbit. So for example, you have a complicated system of ODEs with a complicated boundary conditions, but you already know, you can guarantee that around each singular orbit you have local solutions. And so, for example, in the design I made, you can find a tubular neighborhood, a neighborhood of a singular orbit, where there exists a solution for the system of ODEs with the boundary conditions. That is guaranteed by this paper, and I think that's very strong, very strong. And in fact, the thing is that you solve the equation, you have these conditions, and they have they have a theorem that say that if you can extend the functions fi satisfying these equations to t equals to 0, for example, then that extension is also an Einstein metric. So these conditions holds in the singular orbit, holds in the singular orbit. You don't have to make a lot of things there. Okay, so now we're going to talk about a little of cohomogeneity and Wang actions on CPN, and how can we construct them. So let's start with a Hermitian symmetric pair of rank 2, UK, and denote by U and K the Lie algebras of the groups. Okay, so if you take a Cartan decomposition of the Lie algebra of U, the K plus P, you can prove, and it's classical, it's a classical result that there exists an element Z in K such that the adjoint representation of Z restricted to P is a complex structure on P, okay, and it is invariant with respect to the adjoint representation of the group K. So in this case, if we have a complex structure here, we can identify this subspace P with a complex space C n plus 1 with copies of C. Okay. So you have this action of K on P, that is the adjoint representation. This one can prove that this is a cohomogeneity and Wang action. And since this P is identified with Cn plus 1, then this action induces a cohomogeneity and Wang action from K to the projective space of P, which is the complex projective space. So by an identification, this is a complex projective space. And the adjoint representation, this action is of cohomogeneity 1. And this is a way you can construct a cohomogeneity 1 action of a group on a complex projective space. And the interesting part is that we have this theorem by Takagi, I don't know how to pronounce that, Takagi in 1973, that says that essentially this is the way you construct all the cohomogeneity 1 actions on a complex projective space. Then specifically, we have if G is a compact connected group acting on a complex projective space with cohomogeneity 1, then the action is orbit equivalent to an action, a cohomogeneity 1 action induced by a Hermitian symmetric pair, as we said before, in this way. Okay, and here I want to point out that what means orbit equivalent? Orbit equivalent. In what sense this characterizes all the action, all the cohomogeneity 1 actions on complex projective space? In the sense that the principal orbits are diffeomorphic. If you have an action, a cohomogeneity 1 action on a complex projective space, then that action is orbit equivalent to a cohomogeneity 1 action induced by a Hermitian symmetric pair, in the sense that the principal orbits of the action are diffeomorphic to the principal orbit of the action induced by this pair. Okay, And also, he classified all the symmetric pairs that induce cohomogeneity one actions on complex projective spaces. So you have this table, you have 5 models of cohomogeneity one actions on complex projective spaces, and they are induced by these symmetric pairs. This the algebra, this the algebra, this the algebra. Here, with this table, you can start. So maybe if you can take, you can study Einstein metrics of preserving an action of cohomogeneity one on complex projective space. That is a good idea because you have this table. So you have essentially all the cohomogeneity one actions of on complex projective space. So I'm going to give an example of a partial result we have. And we take, for example, the model C. You have the pair SOM plus 2, and K would be SOM plus R. This action is equivalent to, for example, this action. This is an example of the model C. You have the special orthogonal group of dimension n plus 1 acting on CPN with cohomogeneity 1. So the action is the natural one. You have a matrix n plus 1 times n plus 1 matrix, square matrix, and the action on the class of an element would be the class of the matrix times the vector. You have the class of a vector in C plus 1, Cn plus 1. So this natural action is an example of model C action. This is in this. And in this case, I think it's good because we can construct the geodesic. For example, we can parameterize the complex projective space C from 0, 1 to CPN with this curve. This is the class of the vector 0, 0, 0, and the last two coordinates are 1 minus t and the square root of minus 1. And you can work with this action to determine, for example, the isotropy group. Isotropy group would be H. A principal isotropy group that we call H is the isotropy group of an element of this group with t equals to with t different to 0 and different to 1. We can prove that this H is equals to the special orthogonal group of dimension n minus 1 times the group of two elements. Okay, and you have the singular isotropy groups. This is an action that have no exceptional orbits, and the singular orbits, you have the groups of the singular orbits. Okay, this is the singular orbit at 0, and this is the singular isotropy group at 0 and this is the singular isotropy group at 1. Okay, so for example, you can see a principal orbit at this as this homogeneous space. And the thing is that, and the singular orbits are equals to this homogeneous space. One can prove that this one is diffeomorphic to the real projective space, and we have the singular orbit diffeomorphic to this. Okay. So as I said before, the only thing that you have to do in order to find the Einstein equation is to give a reductive decomposition of this homogeneous space here, this principal orbit. And how can we do that? Okay, I want to mention this is that for example, the quotient K plus over H is a sphere, As I say, these two quotients are spheres. We already know that. But one is of dimension 1 and the other is of dimension n minus 1. So let's see how can we construct a reductive decomposition of the Lie algebra of G with respect to this principal orbit. We can take this inner product that is nothing but the negative of the Killing form, rescaling by a constant. And the isotropy representation of this singular orbit, G over H, decomposes into three irreducible invariant subspaces. So as we know, a diagonal metric on the homogeneous space is determined by three parameters. These are three parameters. And we have that for each T. So we have a metric on the complex projective space of cohomogeneity 1 with this formula, where T is in the interior of the closed interval 0, 1. Okay? And if we write the equations, the Einstein condition, using the formula for the Ricci tensor given by Grove and Ziller, we have that the Einstein equation in this case is this complicated system of differential equation. We have this equation, this equation, this equation, and we can translate the boundary conditions to obtain these boundary conditions. And here we have a difficult thing to do, because this is not a simple system. This is very complicated system. For me, it is. And you have these boundary conditions, the conditions that I think they are a little restrictive. But if we analyze this system, it is guaranteed that you have local solutions. But what about if you can construct a global solution, a solution of this Cauchy problem on the whole interval? We have a result about that, and this result is a partial result of the current work, is that there exists no SOM plus 1 invariant Einstein metric on CPN, at least not globally defined, because locally defined around the singular orbits we have, but no globally defined. And basically what we are saying here is that this system of ODEs with these boundary conditions has no global solution. To do that, I'm going to give a sketch of the proof. The thing is that we are, as we say, we can guarantee the existence, the local existence of the system of differential equations with the initial condition at t equals to 0. And if you made a change of variables, you can prove that solution is unique. It's also unique. So you have existence and uniqueness of the equations above with the initial condition at t equals to 0. That's the first step. The second step is to prove that solution lies on an invariant surface. So we found an invariant surface of the system of differential equation. We proved that solution must lie on that invariant surface. But the thing is that invariant surface, how can I say? If the solution were global, the solutions were global, then the invariant surface must fit well at the boundary point in t equals to 1. But that does not happen, because that invariant surface is a closed set, and when you say, if you suppose the solution satisfies all the two conditions, then these last conditions, the boundary condition at t equals to 1, does not belong, this initial condition does not belong to the invariant surface we found. So that's the thing we can guarantee, that there is no a globally defined Einstein matrix on CPM. Okay? I don't know if it is clear, but I hope so. Okay? So that's a result, a partial result we have. And I want to give a few further remarks. And the thing is that the metrics we are dealing here, for example, this SON+1 invariant matrix, I say SON+1 invariant matrix, but the metrics are not homogeneous because the action is not transitive. So at least we can say that the metrics are not homogeneous, are inhomogeneous. And we did a similar approach, a similar argument from this example to the model A. The model A have a similar behavior. You can also find an invariant surface that does not fit with the final condition. The initial condition fits, but the final condition doesn't. So you have a similar analogous result on the model A. The analysis of the other models, B, D, and E, is part of a current work we are dealing with. I think it's a very difficult work because the analytic tools, in my opinion, are strong. For me, it's difficult. But preliminary results suggest that we can construct a globally defined Einstein matrix for that model, at least for the models B and D. Okay? And the other remark is that the boundary conditions, these boundary conditions for me are too restrictive. So in general, I think that globally defined solutions, in my opinion, are not common. But that's a personal opinion that is not based on any proof or any result. Okay? And the thing is that seeing to the future, I think that we can make some approaches for other families. For example, we have the classification of cohomogeneity one manifolds on complex projective spaces, but we have results, similar results, for example, for symmetric spaces. See, symmetric spaces we have in some classes of symmetric spaces, we have classifications of cohomogeneity one actions on those classes. So I think this is a starting point because we can make some work with some results on Einstein metrics or other geometry issues for families of cohomogeneity one manifolds. Okay, so here are the references if you want to see. And that's all. Thank you.
Okay, thank you very much, Brian, for this very nice talk. Let me upload here. Okay, then are there any questions or comments for Brian? Yes, Diego, please.
Yeah, so you proved that there are local Einstein metrics on this cohomogeneity one manifold, and you say you can't make it compact with the topology of CPN, but can you conceivably obtain a complete Einstein metric by adding a different singular orbit at the other end?
Sorry, I didn't get your question. You said if I can get a globally defined Einstein metric with respect to
because
other
you have CPN, you use that as a cohomogeneity one manifold. Yeah. If you remove one of the singular orbits, I mean, do you get an Einstein metric on that?
Okay, just removing one singular orbit.
Yeah.
Well, I don't know really, because you have the invariant surface, but I don't know. We don't know, and I think we don't know how long is the interval of definition of the solution.
Yeah, okay.
So,
Because then the question would be whether you can possibly, replace the singular orbit which goes wrong with a different singular orbit and obtain something which is Einstein and compact.
okay, no, that is interesting. So maybe I don't know. I was looking for literature about the interval of solution of an ODE. I think that is not trivial, but maybe using the symmetry of the manifold or some geometric result, we can say something about that. But
Well, you don't have explicit solutions, right?
no, I don't know.
Okay.
I don't know. We know that there is solution, but we don't know how long it spans. Thank you for your question.
I have another one, actually. Can I? So is the Eschenburg-Wang theorem really completely general? I mean, the one about the smoothness of the metric at a singular orbit? Because I thought they had some technical assumption on the fact that the tangent and normal direction don't have a common representation.
Yes.
And I mean, I know there's more recent work of Verdiani and Ziller on that. I mean, Verdiani and Ziller have studied the problem in greater generality, I think. I mean, I don't know if you've read. I'm not really familiar with that work, but I was asking for a comment. I mean, because can you comment on that?
Yeah, the result from Eschenburg and Wang is not general. General is not. It has a restriction, but it's a technical restriction that, for example, in the cases we are dealing, there is no problem with that. But it is not general. It is not general. You have the reason.
Okay, I see. Thank you.
Thank you.
Okay. Are there any other questions for Brian?
May I
yes.
ask a naive question? What could we say about the geometric evolution of inhomogeneous Einstein matrix? Well, how it will be in, for example, if we look at the Ricci flow for geometric, for Einstein matrix, how it would we be for inhomogeneous Einstein metric?
No, I don't know any about that. Maybe we can. The thing is that in this case, you consider, for example, the Ricci flow with non-homogeneous initial metric. You have a PDE, and about the evolution of the flow, for example, of the metrics in that case, I don't know. I haven't studied that. And I haven't seen results about that. Oh yeah.
Yes, I know there is no results about it. So I was very curious if what could we can say that about non-inhomogeneous initial metric about for Ricci flow, and I think it would be very good, interesting.
It is. In fact, I think so. Yeah, but I don't know. I know that I can give you a reference from Renato Bettiol, and he deals with the Ricci flow of cohomogeneity one metrics on 4-dimensional manifolds. It's a very interesting paper, and maybe you can find some result about that there.
Well, yeah, I am very interested in for Ricci flow for different kind of metric, Einstein's metrics. So your case is very interesting for me. I was hoping to understand how it will be for your inhomogeneous Einstein matrix under Ricci flow.
That's nice. I appreciate that question because I can look forward to problems related with.
I imagine it is a very hard question.
Mm,
Very hard question.
I think it is.
Yeah, thank you. Thank you very much for your nice talk.
Oh,
Very
thank
good.
you.
Thank
Thank
you.
you.
Okay. Are there any other questions? No? Okay, well, thanks again, Brian, for this very nice talk.
Thank you very much.
And